Hello everyone, my name is Christopher Wade and we're going to talk about embedded mobile chipsets today and how you can write custom firmware for them. I am a security consultant at Pentest Partners, where I mainly work with automotive hardware and maritime equipment, but today we're going to be talking about embedded chipsets in their entirety, especially on mobile devices. The origin of this project was that I had rotated several phones and found that while I could modify certain aspects of the operating system, I couldn't modify the hardware capabilities of them in any meaningful manner. While it was still possible in certain ways, it was not possible in their entirety, so I couldn't modify certain closed source and closed hardware elements of the devices, such as hardware peripherals such as Bluetooth. While it is possible via certain kernel modifications or changes to configurations to get monitor mode, it does require custom firmware for things like Broadcom chipsets. USB device emulation as well is quite an interesting feature that can be added to Android phones with a certain amount of effort. If you modify your kernel so that it implements all the USB functionality modules that you want instead of just the static one for Android, you can implement things like GadgetFS, which allows you to emulate any kind of USB device you want via user space applications. But I wanted to talk about NFC more than anything, which is something I'm very interested in and is quite limited on Android hardware as it is. For instance, on Android, even with root access, you're limited to generic reading, mobile payments, NDEF communication, and host card communication, the last of which is communication that allows you to emulate certain amounts of NFC tags, but not in their entirety. While this allows you to do certain things like relay attacks, which may be useful for an attacker who wants to commit fraud, etc., it's not very useful for other use cases. If you were to make an NFC attack tool, you would want to implement slightly more complex functionality, such as emulation of a reader to attack cryptography on an NFC tag, or emulate the tag itself in order to perform attacks that are only possible from that endpoint. Or you may want to be able to passively sniff tags like you would with a Proxmark or a Chameleon device. My first target was my Samsung S6, which is quite an old phone, but one I had readily available and unlocked using the standard Samsung OEM unlocking and custom ROM functionality. I found that in my Samsung device, which was a non-US phone, it had a Samsung semiconductor NFC chip that was completely custom and developed by Samsung for their devices. This was called the S3FW RN5, which was a custom chip developed by Samsung Semiconductor. It has the ability to update firmware securely and is found in Samsung S6s and Samsung Note 4 devices, which were manufactured in 2014 and 2015. It was found to use an ARM SC000 secure car architecture, which is a embedded ARM architecture used for secure applications, and is communicated with on the phone via custom device drivers which communicate with the I2C and GPIO interfaces of the device. NCI communication, which is how NFC chips are communicated with via host devices, is quite a simple protocol. Essentially, you have a group ID, operation ID, length and payload, which are used in conjunction to configure certain settings or to read certain data from the device in order to configure specific NFC functionality. While this does make NFC quite simple, it also restricts it quite heavily. There's also non-standard functionality built into this protocol, however, such as vendor group IDs, which are group IDs which allow a vendor to implement any functionality they need whatsoever. They may use this for configuration of certain hardware that's not standard, or they may use it to add certain debugging functionality that they'd want later on in the project. But what this is never used for is firmware updates, which is a key aspect of any embedded chipset. The device itself was found to set whether it was in bootloader for firmware updates or regular mode via a GPIO input, which could be set via the driver. And I found that when you switched it into bootloader mode, it had a slightly different protocol than NCI, but only slightly different. What this was used for was to differentiate itself from NCI in order to allow the vendor partition and the vendor implementations of certain aspects of the firmware to update this chipset and use it to do different things. This firmware update protocol was quite simple. I pulled these traces from logcat just by running logcat while doing a firmware update, and found that it was made up of a command type, which was usually 0, 1, or 2, a command, which was based on what aspect of the firmware update was being performed, and a payload size, which was 2 bytes, but was limited to only 256 bytes in total, as well as a parity bit at the top of each command and type in order to set where they were in the firmware update process. The firmware update files used had a very basic format. They had some metadata highlighted in red, which was the date that the firmware was made, a signature, which is highlighted in green, which was just a simple RSA signature, and highlighted in blue was the start of the firmware, which I found to be standard ARM update firmware. There's a way to identify this quite quickly just by using a simple mnemonic. If you run strings on a firmware update that's unencrypted and search for the characters lowercase p and uppercase g, you'll quickly find that a lot of these get dumped out if it is using thumb code, which is the shortened architecture used by ARM. Because lowercase p and uppercase g translates to 70 and 47 in ASCII, which is the XLR or branch and link operation used by ARM devices in order to return from functions, you can quickly identify lots of areas where this has been used. When this is found in large quantities, it usually means that it's using ARM firmware. A good way to implement firmware updates is just by replaying all the commands that you've dumped in sequence. You don't necessarily need to know how the protocol works, as long as you can send commands in exactly the same order as they sent before. These things are usually immutable just due to how the signature checking and hash checking are implemented. What I did was use that logcat and made a huge number of byte arrays and cycled through them while making sure that in IO controls used pulled from the open source kernel drivers for this chip were used. Looking at this further and looking at this open source driver, I found that it had commands well defined in there for me to look at. So command 0 was defined as reset, command 1 was boot info, command 2 was beginning the updates, command 4 was to update specific sectors, which included a address and the data itself, and 5, which verified the signature and hash together in order to complete the update. Because there was no command 3, it made me think that there were some hidden commands that weren't used by the firmware update but may have some extra functionality. I could easily identify hidden bootloader commands just by seeing what errors were returned by the chip when I sent certain commands. If it returned 2, it meant that the commands were not valid at that stage of the firmware update process. And what I did was process through each step of the firmware update process while using these different supposed command states. However, if the chip returned 9, I was able to see that the payload was just too small, and if I increased the size, eventually I'd get a different error which would let me know the minimum size of the commands being sent. Brute forcing through this allowed me to find that command 3 was just a different version of command 4. However, instead of sending the 4096 blocks used by command 4, it sent 512 instead. However, command 6 was also noted and was much more interesting. Command 6 was found to take 8 bytes of parameters, which was two 32-bit values. By setting random bits inside these parameters, I found that it would dump out arbitrary memory from the chip, and allowed me to work out that this was taking an address and a size for data being returned. Using this, I could dump RAM, firmware, hidden hardware registers, and the secure bootloader, meaning I could reverse engineer this. I stitched this bootloader together and found that it used a standard Cortex-M firmware format. So this would be the start of, the first bytes would be the start of the stack, and the next bytes would be the reset vector used to start up the chip. Looking at these together, I could easily disassemble this in any disassembler I had. However, because this is an embedded firmware, it had very few strings and I'd have to look at everything by hand statically. There are a few interesting artifacts in here. So all the firmware that was deployed was found to be stored starting at address 3000. And in the firmware itself, I found that the first 4 bytes of the firmware were always FF. However, I found that the firmware update would overwrite this with 5IF00FA5, which was found to be a magic number used to verify whether the firmware update was indeed valid and the signature had been checked during updates. I tried to stick this particular value in straight away in a completely invalid firmware and found that this didn't work, and that the bootloader checked whether the first value was always FFFF. I also found the state machine which checked which commands were being received. So we have 0, 1, 2, and 6, which were the commands that were available at the start of the firmware update process. And I could look through to see that there were no other commands that were in use during this process. I also noted the RSA public key in memory, which was interesting but not useful because it was quite high entropy. This can be easily identified by looking for 00010001, which translates to 65537, the exponent of RSA public key. And before this is usually 128 or a different size of high entropy bytes, which usually denote the modulus of the RSA public key. Now, because I now had the bootloader, what I really wanted to do was find a memory corruption exploit in this bootloader, allowing me to have an immutable, unchangeable way of adding custom firmware to this chip whenever I wanted to. Now, fuzzing my phone seemed like a bad idea at the time, mainly due to the fact that if I broke the chip, I'd have to buy a new phone to look at it, or find a way to unbrick it, which would involve some hardware modification, which I didn't want to do. Also, due to the fact that the only endpoint I had into the device was I2C, debugging and analysis would be very difficult. Due to this, I decided to emulate the bootloader as much as I could. I decided to use the Unicorn engine for this, which is a library which is very powerful and allows one to implement different firmware types using different architectures in order to assess how it works and also run functionality that wouldn't necessarily be possible on the architecture you're using. It's sort of like a form of QEMU, except inside applications rather than something to run applications themselves. I loaded my bootloader into address 0 as it would be in the actual device. I set the program counter to the reset vector, which is found in the bootloader, and I mapped memory for hardware registers, RAM, and flash ready to start fuzzing this protocol. However, a key aspect of this was the fact that even though I'd used Unicorn engine, I wouldn't be able to emulate the hardware as easily because it just simply didn't exist and it was completely new and no one had ever seen it before, especially in this format. What I did is let the firmware run until it started reading from the hardware addresses, which start at OX4000. I found that it started reading a specific address during startup and was checking for specific bits in the firmware in this register in order to identify certain aspects of the status. I'd worked out that this was the status register for I2C, so I made this always return randomized data, meaning that the status of the I2C bus would be deemed to be doing something at the time and would move past this state. Next, I found the firmware continually reading bytes from another address, which was close to the original, and found that this was likely to be the I2C FIFO buffer due to the fact that it was loading any bytes inputted from this into a buffer. I started sending firmware update commands via this register by hooking into Unicorn engine, and found that it would then start sending data on another address that was close in that area, and found that this was sending responses to my I2C messages as the bootloader would have. Because of this, I had full emulation of the I2C communication of the bootloader and could start fuzzing it as needed without having the potential of breaking my chip. I started randomly fuzzing the chip, but found that it wasn't really viable and didn't do very much. While commands have 16-bit sizes and largely the entire contents of RAM, they were limited to only 256 bytes, and I couldn't do much with that. I did find that some commands would send additional data in chunks. For instance, when you were sending 4096 bytes of update data, these were chunked into the 256 bytes that were permitted by the protocol. However, I also found that the size of the hash and signature, which was sent subsequent to the hash and signature command, were defined in this command and were modifiable. By increasing the size of the hash and signature sizes, I could allow myself to send more and more data subsequently. For instance, if I said that the hash, the SHA-1 hash, was 200 bytes instead of the classic amount, I would be able to send that much data. What I found was, in my emulated chipset, this overwrote the stack and hit a invalid aspect of memory, so over the 8K of memory that was available. Because I could overwrite the stack, I could change where the return pointers were in the stack and change where the program counter would jump to after returning from these commands. Due to the fact that the secure core SC000 chipsets can't execute from RAM, I wouldn't be able to do anything simple like just write a bit of shellcode. Also, because the stack was so small, only being about 12 bytes at this point, it was too small to do any complex ROP exploits. In order to get past this, what I did was just make it jump the program counter into the signature checks at the start of the bootloader, past the checks that actually occurred, and into the part where it loaded the address of the firmware and jumped into it, which restarted the chip into the core firmware. I then performed this exploit on the physical chip and found that it worked beautifully. So I booted my bootloader, sent my exploit, and then noticed that after I'd run it, it would start behaving as the real firmware, and I could send NCI commands instead of firmware update commands to the chip. What I did was simply change the version number of the firmware just to show that this signature checking had been bypassed and that I could run my own custom firmware. I then disclosed this to Samsung. Now, there are two ways they could have fixed this. Now, because it was a bootloader level exploit, it's a bit more complicated than just updating the firmware. They would have to patch the bootloader from the main firmware, removing this buffer overflow vulnerability. However, while this was being undergone, if someone power cycled the chip or there was some kind of error, the bootloader would be left erased and they would never be able to restart it again, leaving the NFC functionality of the chip completely non-functional because the chip wouldn't be able to start. or they could have patched the kernel to disallow large hashes in signatures. However, this was trivially bypassed just by kernel modification if they did that. I decided to look at other NFC chips that Samsung had used, or developed rather, and found that there were 4 that were in modern use: the S3NRN74, S3NRN81, S3NRN82, and SEN82AB. I wanted to find these chipsets in different Samsung phones to see which one I should purchase in order to continue this research. Now, because teardowns aren't always available, especially for non-US devices, it wouldn't be a simple task of just Google searching for these version numbers and phone types. So what I ended up doing was going to sammobile.com, which contains ROMs for almost every Samsung device, downloading them, extracting them, and finding whether they had the firmware files embedded in them. These were usually found in the /vendor directory, and occasionally this is a separate partition, but generally it's easy to find. Looking through this, I managed to find the S3NRN82, which is used by the Samsung S9 as well as the Samsung S8 and Samsung S10. However, I decided to buy a Samsung S9 for this purpose. I found that it had multiple chip firmware revisions just by looking at different ROMs, which would be very helpful if I needed to reverse engineer more. And I found that the Samsung S9, while it was secure from a routing perspective, you could use OEM unlocking and a custom ROM in order to route it appropriately to perform any attacks on it. The firmware file was found to be almost exactly the same as the FWRN5, at least in formatting, so it had the same metadata signature and firmware payload. However, the reset vector of the firmware, which was found at the top of it, was much smaller, implying that the bootloader had been modified to be smaller, and the firmware size was 32 kilobytes larger, which was corroborated with what was on the datasheets on Samsung's website. I found that commands 3 and 6, these being the smaller deployment of code command and the firmware readout command, were no longer available. However, command 7 was identified, but all it did was reboot the chip. A new bootloader size implied that the firmware bootloader had been modified in some way, meaning that I'd probably have to do something a bit different in order to exploit this. And due to the lack of memory readout, verifying what I'd done before would not be as easy, and I'd have to do any exploitation blind anyway. Also, I found that trying to upload firmware using a SHA-1 hash was not possible anymore. Because because the I2C communication was no longer provided by logcat, I had to go looking around to see how this was logged, and found a device file called /prog/nfclog, which contained the sizes of all the commands being written to the chip in sequence, and found that at the start of firmware updates, a larger hash size was written. So instead of the SHA-1 hash size, it was now sending 32 bytes plus the header of a command, which was 4 bytes. This implied that instead of using SHA-1 hashes for firmware updates, they were now using SHA-256 hashes, which were compared against the signature. I verified this by modifying my firmware update tool. Because I no longer had any knowledge of how the inner workings of the bootloader worked on this new bootloader, I would have to guess quite a lot of how the exploitation worked. Due to the nature of device crashes, I could work this out, however. I decided to attempt the exact same exploit I did before by increasing the size of the hashes until I overwrote the stack. What I did was keep adding more and more size to this to the size of the hash, while sending more and more data. Now, due to the nature of how the stack worked in this, it would still return data even if I'd overwritten the stack, but then crash. However, if I'd overwritten memory, that being over the 12K that was now available, the device wouldn't return after I sent data to it, meaning that I'd be able to work out the entire size of the memory I was accessing and overwrite it with any data I wanted or any return pointers I wanted. Here's a quick demo of how this worked. So because I didn't know how where the program counter needed to jump to in the bootloader anymore, by virtue of the fact that I couldn't see the bootloader, what I ended up doing was processing from address 1, or rather program counter address 0+1, which is how thumbcode addresses code in this manner, and let it run until it found an endpoint, address which would allow it to jump into the raw firmware. We're hitting the end of this now, so what this is doing is filling the entire stack with return pointers, because I also didn't know where the return pointers would be. And what I found is when it got to address 165, that was the correct position for it to jump into the unsigned firmware, and it would allow me to bypass the signature checking. I disclosed this vulnerability to Samsung as well, and they have now patched it on all newly manufactured chipsets from April 2020, and all future chipsets will be patched so that this doesn't occur. However, older chipsets will still be attackable using this approach, and will still allow custom firmware to be developed. So, because I could write custom firmware for any of these chips, I decided to aim for the STNRN-H2, as this was the newest, the fastest, and had the most memory. Because I'd only be able to debug things via I2C, it would be quite complex to debug, but at least I had something to work with. I downloaded a firmware file that I found inside a Samsung S8 ROM, this being the oldest phone which used this chipset. I found that it had quite a lot of spare memory compared to the firmware that was used on the Samsung S9, and I could use this to patch in machine code that I'd compiled as needed. In order to do this, all one needs to do is compile C functions using gcc-c. All this does is create an object file without any linking or relocation, but gives you raw assembly to work with, or rather raw machine code. Stack handling is still handled appropriately with pushes and pops, as any ARM code would. However, you would need to implement any C standard libraries yourself, so any mem copies, any string copies, and comparisons would need to be done by hand. So in C and ARM, function calls are all generated as branch and link instructions. So what happens is functions are called by jumping to a relative address compared to the current address where the program counter is, and then it usually pushes some registers and then pops them at the end to return back where it was. This can be used to patch out existing functions in the firmware, or even override them completely as needed in order to change functionality. Branch and link uses two complement relative addresses, which is some simple binary mathematics, but can be used to jump relatively from the current position into where you want to be, and can be patched over any existing branch and link functions, basically. So if I wanted to change one specific function to do something else, I could jump to my own functions into that empty area of memory where I'd patch them into. I made a small build application for this, which literally did all the linking and relocating for me by dumping out function calls from my binaries and relocating them as needed, as well as performing manual ARM patching as I needed to. First thing I wanted to do is make a I2C function which would allow me to read arbitrary memory. And what I did was select a specific vendor-specific command, this being 2F24 in the firmware, which was used by some unknown functionality of the device, but was essentially allowed arbitrary size of parameters and was allowed to be run continuously as needed. What I could do was modify this to do what I wanted to. I searched for mov 0x24 using regex in IDA, which literally let me find exactly how this was loaded for setting up response headers, and then I overrode the function that was right before the send function in I2C, so that it would jump to my get arbitrary memory function, which would allow me to jump read memory or modify memory as needed to whenever. Because writing a firmware took around 20 seconds, this was quite a difficult task and took a while to set up, but when it did, it could be expanded as needed. Because I could now send data back, I wanted to take parameters as well. I didn't know exactly where the parameters were stored in RAM, just by virtue of how complex the firmware was. So what I wanted to do was quickly find this out. And I did this by crafting an NCI request, which had 2F2404, FACE, FACE. Now FACE, FACE is just a nice little placeholder, which I could search through in RAM in order to find the address of these parameters being sent. And I used this to find exactly where this was, so I can now send and receive commands as needed via I2C with very little code changes. The first thing I did was dump the bootloader, which was very helpful, and I looked at what I was actually hitting with my exploit. Because I hadn't seen this bootloader before, I didn't know what I was hitting to make this work. What I found that what the bootloader was doing was loading from R0 into R0 from the address. Now, because we had jumped here directly from the function call, we had no idea what R0 was. And so the fact that this worked at all was quite impressive. What I did was change this to address 173, which was exactly the same as where we had put it in the original bootloader, and allowed us to jump directly into the firmware without any problems. Now, reading out memory is very useful, but because this is an NFC chip, I wanted to make it do cool NFC things. Because the chipset supports multiple protocols such as ISO 11443A, ISO 14443B, and a few others that are all in the 13.56 megahertz range, I wanted to implement one of those myself, and I decided to emulate a MyFair Classic tag. as my first project for this chip. I would need to know a lot about that hardware register to make this work, but doing so would allow me to work with the chip in ways which would allow me to emulate any NFC tag. I used a Proxmark for debugging throughout, as I could see how NFC was working at a very raw level, and this was very helpful. I took all the NCI commands that were sent by the phone to the chip usually, and just dumped them into a byte array and replayed them. I then went through each one and found out any of them which weren't actually required for the chip to run as I needed it to, so that I could reduce bloat on the commands being sent. And then I used what I discovered to be the RF discover command, which was the last command sent, and took away all the parameters which set it up into NFC reader mode, or used different protocols, and just kept it for protocol 80, which turned out to be the my ISO 1443A tag emulation mode. Because I had no data sheets to work with and the hardware registers were quite complicated, I'd have to look around in the firmware to see how these were used. And as there weren't any strings, I would have to infer anything I was working out directly from this hardware. The first thing I wanted to do was find out how enumeration works on the chip. Now, enumeration on NFC works largely the same as standard communication in NFC. However, there are some differences which, in speed, which meant that the chipset was probably doing this separately or in some hardware level compared to just doing the standard communication. The first thing I did was search for the select command, which is the second command sent during enumeration, just because I thought this was more likely to work, just by regex searching for comparison and 93 being the select command. This found an immediate result, loading from a hardware address 40020200, and comparing on that value, meaning that I'd instantly found how this enumeration was being selected. I placed the phone on a reader and let it constantly run, and then started dumping from this hardware address using the I2C function that I'd implemented earlier. This corroborated my results from IDA and found that the reader was constantly sending wake-up commands, which are hex 52. This allowed me to also work out other things about the hardware registers, such as the size and certain other configurations I could dump out later. This functionality would allow me to do one-way passive sniffing as well as some other things. It was very useful for getting the emulation working. ISO 14443A communication works in a certain way for enumeration. It requires three key aspects. So what happens is the reader sends a wake-up or a request command. The tag sends an ATQA command, which gives initial information about how the tag is configured or what kind of tag it is. The reader then runs the select command, which returns a UID, which on phones are forced to be randomized, except the first byte, which is always 08, to prove that it's not a real tag. And then a SAK command to give information about whether the UID is slightly larger and needs further enumeration or any other changes. Via NCI, I could modify this to a certain amount. However, certain bits were set in any ATQA value and stack value I sent, which meant that it was restricted to always being known as a phone. I found out later that these values are probably stored in individual hardware registers, and I need to find out how this worked. I sent specific values to the chip and then searched through RAM to see if I could find where they were stored in RAM. I then compared this to IDA and found where the addresses of these were compared with hardware addresses. And I found this function which loaded each SAC and ATQA and UID value into certain addresses. This would give me quite a lot of insight into how hardware works, and I could modify it as needed. I overrode this function and then called it from within the new function I'd made. This would allow me to set up all the hardware as I needed to without me needing to do it myself. What I then did was overwrote what they'd implemented into the hardware, so what UID value and SAC and ATQA values they'd initialized, and put my own ones in. I then confirmed this using a Proxmark as a reader to prove that my new UID, SAC and ATQL values had worked. When I looked on the Proxmark, I found that this was successful and allowed me for modification of any enumeration. So I made a custom 7-byte UID, set it up to pretend to be a MyFair Classic mini tag, and yeah, worked absolutely beautiful. But it would not allow me to do full communication. It wouldn't allow me to emulate the MyFair Classic part of the MyFair Classic communication, just to pretend to be one on a superficial level. I knew that the chip would respond to halt and RATS commands, RATS commands being some more configuration data being returned, and halt commands being a more high-level communication aspect of the enumeration setup. I searched for the RATS command using comparison E0, which was the command used by NFC for that particular functionality, and found 4 results and just looked through them and worked out which one was which, and found the specific one which was in use. This led me to find the exact state machine that was used by the chip to do further communication, and also found some further valid commands. Further tracing of this found how it would send responses. So I found how the hardware registers were set up. So I found that it was using the same hardware address space as the rest of the NFC setup, so 4002.0000. However, I found that the length was set up at 08 in this address space, and that the data itself was set up at hex 100 in this address space, which was just underneath hex 200 where data was received. So the senders and received were quite next to each other, but also had quite a lot of space to do what they wanted to. I wrote all these registers out and dumped them into a new function, which I could then use to modify as needed. A basic read command was then implemented, which is always used by NFC, which in MyFair Classic and MyFair tags in general, which is 30 and then a block size and then a CRC, which is just a standard unencrypted read. While MyFair Classic does encrypt these requests, and we'll come to that later, some standard MyFair tags do not, and by implementing it I could prove that I could do full communication on this chip in any way I needed to. I overrode the entire state machine, added my own functionality, so I could add in write blocks, read blocks, and authentication commands used by the MyFair Classic, and I also re-implemented the halt command so that it called the halt command in the actual firmware at 5E09, so that I didn't have to affect the internal state machine of the hardware too much because it was set up by this. I also added some non-standard debugging commands such as 70, which allowed me to dump out raw memory from the chip via NFC, so I could do it via I2C or NFC as needed. With this full control, I could emulate any ISO 14438 tag. I stuck with the MyFair Classic, but I could expand this quite a lot. The full authentication mechanisms which are implemented, which are quite old but quite simple. It authenticates using sort of a standard key, which provides some level of mutual authentication. And while it did work, unfortunately, because I was loading 8-bit buffers into the responses, there was no space to modify the parity bit, which is quite heavily used in MyFair Classic as part of the encryption. How this works is every 8 bits has an extra bit in NFC communication, which is used to check the parity of the previous data and just to make sure that there's no communication errors whatsoever. Now, this, as standard, was found to be implemented in the hardware of the chip so that you didn't have to bother with this in software. However, I found that this meant that I couldn't modify the firmware at all in order to fully implement MyFair Classic, because no standard reader would look at this and think that the encrypted parity bit was correct and think communication was broken. However, I thought it was very likely that there was a hardware register somewhere which would allow for modifying of this parity bit in myself. However, this would mean pushing 8-bit and 9-bit buffers around in some complex ways. I modified each register used by the hardware in turn and see if any responses were changed. Now, it had a few interesting outcomes, like it increased the sizes of the responses in weird ways, or added strange CRCs I'd never seen before, which all seemed to have some functionality which was unrelated to what I was trying to find. However, I found address 4002.0004 by setting bit 4000. I could modify the parity bits as needed. All I had to do was change the size of the responses I was sending and send an extra bit per byte, meaning I was sending 9-bit values into 8-bit buffers, just meaning that things had to be shifted around a bit. With this, however, MyFair Classic could be fully implemented, and I had access to full communication of MyFair Classic, and it worked. I also made the chip send back writes to the MyFair Classic tag via I2C, meaning if I uploaded a file NFC tag to the chip, I could then get changes to it back so that I could have some persistent storage of this data. Now, here's a quick demo of this. All I've done is taken a different phone using the NXP tag info tool, and I've placed it on top of my Samsung S9. And what you'll see is that after a while, after it's checked all of its keys and checked all the authentication, it will come back and show that it was, in fact, identified as a MyFair Classic tag and try to authenticate all of the NFC blocks available. So there we go. Now, I tried a few different keys and a few different settings in here just to make it look more interesting, but essentially this was full implementation of MyFair Classic. Final notes on this are that with this you could spoof any 13.56 megahertz access control. While this didn't include 125 kilohertz access controls, which are still widely used, it was quite a lot of access you could now gain by modifying this setup. However, you also had more esoteric uses which for things like toys and games and things which use this functionality. Despite the fact that I'd patched the firmware, all other NFC functionality of the chip would work as normal. So if I set it back to act as a reader or any other kind of tag, it would work like that absolutely fine. I'd found that this would probably be more subtle than using a Proxmark, as it was more subtle than a dedicated attack tool. It's a phone which no one expects to have any of this functionality built in, whereas carrying around a Proxmark with an antenna is slightly less subtle. Expansion of this functionality would allow you to dump authentication and keys off readers just by virtue of how some of these authentications are implemented. And you could implement it on any supported protocol, not just ISO 14443A, but also 4443B or anyone supported by the chipset. And now that the framework is in place, it would be easy to develop these for. It's simply a case of combining the code now. I outlined all of the vulnerabilities and the patches I'd made to Samsung, and they'd patched this out in their current chipsets as of April 2020. That means chipsets of this version that were manufactured after that date would no longer be vulnerable to this, but there's still plenty about that are. The vulnerability did require root access, which meant that the phone wouldn't be compromised by this attack, but the chip was compromised in ways that would make it much more useful than it would be as standard. We have to remember that phones are exploitable embedded devices. You can treat it like any IoT device you're attacking as long as you approach it in the right way. While the security may be higher, there's definitely some interesting things you can look at, especially bootloader vulnerabilities. These are increasingly common, and just by virtue of the fact that bootloader vulnerabilities are in the bootloader, they're going to remain for years because no one can patch them out. You've got to think of things like the Nintendo Switch exploits, which had to have full hardware revisions and still have switches out there which are vulnerable to bootloader-based vulnerabilities. Developing custom firmware for proprietary chips like this is interesting and challenging, but it's also rewarding. You can make some really interesting stuff happen with this. You've got to think about also things like Broadcom chipsets, where people have added Wi-Fi monitor mode at a later date, or modification to things like Bluetooth chipsets, where you could add extra debugging functionality. And lastly, if an undisclosed vulnerability is found in an old chip, it will likely be in a new one. Thank you very much. Hello everyone, thank you very much for coming to my talk. I hope you enjoyed it. Now, I've seen a couple of questions in the chat that I'm just going to briefly go through and hopefully answer them for you. Firstly, I had a question regarding mobile payments. Now, due to the nature of this vulnerability and the fact that you need to root a phone to do it, it's required that someone would have to intentionally be trying to do this in the first place. Now, when you work with mobile payments, especially with Samsung, you have the fear of tripping knocks and all sorts of other security measures that can be bypassed, but it's much more difficult. The whole purpose of bypassing this particular chip isn't really to affect mobile payments, as it won't really be affected by this, but more to expand the functionality of your phone into an attack tool rather than a device for affecting mobile payments, which is something you wouldn't generally do on a not on a rooted phone anyway. With regards to the question about Cortex-M chips, so the chip itself was using a secure core architecture. Now, this is a more lockdown architecture developed by ARM, which essentially has the same capabilities of a Cortex-M chip, but is used purely for these secure applications where you don't want to be able to do things like access RAM or access protected memory in certain ways. Now, the details about how all of this works and how it's architected is something you need to sign an NDA to get from ARM to do, so it's not something you'll fully be able to be capable of. But you can make assumptions based on what capabilities this particular chip had about what capabilities you would have with a secure core. Now, if it was a Cortex M3 or something of that type, I would have been more able to write things like shellcode right into the stack and jump to it to perform things like adding that magic number to the start of the firmware. So instead of doing that, I could add those features into my custom firmware, which was effective as well. I think that's all the questions we have. If there are any others coming through the chat, please let me know. If not, I think we're all good. And thank you for having me.